As a quick reminder on your periodic tables, these numbers that correspond to energy levels are the numbers that we use when we're drawing the Bohr model for each element that's in a particular period. So your periods, if you get them mixed up, a period is the row. And when I say group or family, that's talking about the column, the vertical. So a family versus a period, this is also called a group. I find myself saying the word group a lot to refer to periods, but that's not what I'm talking about. I'm trying to be really intentional about the vocabulary that we're using. But a family or a group is the column, and then a period is labeled by these numbers across like this. When we draw Bohr models, we use these numbers to tell you how many rings you're going to have. So if you are in period 1, you have 1 ring. If you are in period 2, you'll have 2 rings. If you're in period 3, you'll have 3 rings. And then period 4 will have, it's getting bad. Okay, and so on. So what is happening to the size of the atom as you go down? It's getting bigger. So what we're seeing is as we add rings, this characteristic that we refer to as atomic radius gets larger. So something with 7 rings will be larger than something with 6 rings, larger than something with 5 rings, and so on. So if we go back to page 4 where it talks about atomic radius, as we go down in the period, the radius gets larger. So radii right here, that's just the plural of radius. So if you're going to get confused, you can write radius on here. And just like what it means in math class, hopefully you guys have all had some kind of exposure to geometry, I guess, is when you learn about a radius. It's the distance from the center of your circle to the outside. So for an atom, that's going to be the distance from your nucleus to your valence shell, your outermost ring. And then the other thing that I wanted to point out for our periodic table is what your valence electrons have to do with this. So if we're looking at this, we know that your number of rings gets larger as you go down, so you know that this trend is going to increase going down a group. And then when we talk about in terms of from left to right across our periodic table, our number of valence electrons, we have 1, then 2, skip all these, 3, 4, 5, 6, 7, 8 valence electrons. Let's consider what that has to do with our atomic radius. So if I have something with a, let's choose an element, let's do neon that has 10 protons. I know neon has 10 protons because it's atomic number 10. Neon has 2 rings. I know that because it is in period 2. And neon has 8 valence electrons. So if I draw those 8 valence electrons, keeping in mind that the first one would have to be full too to get to that. Okay. So if I have neon with a total of 8 valence electrons, each of those electrons are being pulled towards the nucleus of the atom due to the negative electron's attraction to the positively charged center. So there's this attractive force that's happening between all of the electrons, not even just the valence ones, and my center. That's just because negatives and positives attract each other. You with me so far? Yes? Okay. If I think of the force that's happening here, pulling this negative towards the positive or the positive towards the negative, however you want to think about it, if I think of each of those as like an elastic band, like a rubber band, and I'm stretching a rubber band here and here and here, and each of them are stretching, if I were to get rid of one, if I snip that rubber band or get rid of that electron, so let's say I get rid of this electron and therefore I no longer have that. is this outer ring able to pull more out and get bigger? Or does it compress more and get smaller? Let's think about that. So if I'm holding on to one end of a rubber band, or one end of 8 rubber bands, and you're holding on to the other end, and I snip one of them, can I pull further away from you now that I snipped it, or am I going to get pulled closer to you? Farther away. So we are going to be able to pull out farther, and as you continue to get rid of them and get rid of those forces, you're able to stretch out more and more and more and more, and it's going to be able to spread out more and more. Does that part make sense? Okay. So with that being said, the least number of electrons that you can have in your valence shell to still have that shell exist is just 1. So if I have something with a positive center, and I have my rings and just 1 electron, there's still a force there that's still being attracted, but it's going to be the weakest that it can be, versus if I had 2 electrons or 3 electrons or 4 or any more than that. So the element on page 4 of your notes, the element that's going to have the highest or the largest atomic radius is going to be the one that has the most rings, so furthest down, and the least number of valence electrons, which is going to be 1. So looking at this, if this is 8 valence electrons and I'm moving across my periodic table, I would be the atomic radius, gets larger moving from right to left. So based on that information, if you look at your actual periodic table that has elements on it, which element would this basically be pointing to? Which element would be left with the largest atomic radius based on this trend? If you don't know how to pronounce it, you can just say the letters. FR. So the element that has the largest atomic radius is francium. We call it Big Frank. And the reason we do that is because it has the largest atomic radius. It's going to be the biggest element on our periodic table in terms of how large the actual radius is. It's not necessarily the largest in terms of mass. It's not necessarily the largest in terms of protons, but the largest radius. If you remember that francium is called Big Frank, then that means the closer you are to Big Frank on the periodic table, so elements that are in this corner generally, are going to be bigger than elements on the opposite side of the periodic table. We can kind of take this the opposite way as well. If we talk about Big Frank as the largest atomic radius, furthest away from Big Frank on our periodic table would give us the smallest atomic radius. Which element would that be? What did you say? So smallest atomic radius. Helium. Perfect. So He is smallest. So helium is number 2 on your periodic tables. Put this picture up. So if we are here, the opposite corner, what's this one? Opposite corner, it's going to be our smallest atomic radius. It's number 2, it's not number 1. But that's on purpose because it's not smallest in terms of number of protons or mass, it's the smallest in terms of the actual radius for the same thing that we described in this picture here. If you are hydrogen with just 1 proton and 1 energy level and 1 electron versus you are helium with 2 protons, 1 energy level, and 2 electrons, the attraction between these electrons and your nucleus, your positively charged nucleus, is greater than the attraction between just the 1 electron. So this one is going to be actually smaller in terms of radius, and this one would be larger. So that would be helium. And then on any quizzes or tests or assessments that we have for this unit, there will definitely be some kind of comparative questions. So if I'm looking between lithium and carbon, which one has the larger atomic radius? Larger atomic radius would mean that I am closer to Big Frank. So which one, lithium or carbon, is closer to Big Frank? Lithium is here, carbon is here. They're both in the same period, meaning they both have 2 rings. This one would have 4 valence electrons. This one would have just 1 valence electron. So which one is larger? Lithium. And then this example says between barium and magnesium, which one has the smaller atomic radius? So if we're looking for smaller, the 2 ways you can think of it are which one is closest to helium or which one is furthest away from Big Frank. Both of those will give you the same result. So between barium and magnesium, barium is down here and magnesium is here. Which one would be smaller, magnesium or barium? Further away from what?
Big Frank.
Barium is here and Big Frank is here.
What's the other one?
Magnesium. Magnesium is further away from Big Frank, which means that it is smaller. Cool. I'm going to do it in blue. Something else that this has going for it is that they are in the same group. So if they're in the same column, that means they have the same number of valence electrons. What you need to consider first when looking at atomic radius is what period something is in. Every single time, something that is in period 7, let's say, will have a greater atomic radius or a larger atomic radius than anything in period 6. Anything in period 6 would have a larger atomic radius than anything in period 5, and so on. So the more rings you have, definitely the bigger you are. Electrons are kind of more of the finer details in it. So if you're comparing left to right, that's what we're looking at as valence electrons.